Hi, we're here to solve an integral calculus problem regarding the work required to empty a tank of oil. I'd say the more amusing side of the theorem and calculation-based calculus would be in its application, and a work problem would be a great example of that. Let's take a look. A spherical tank is half full of oil that has a density of 900 kilograms per cubic meter. Find the work required to pump the oil out of the spout. Now we see on the figure on the right over here, a 3D figure of the tank, that the radius is 12 meters and the height of the spout is 3 meters. So we can start out by considering the oil to be subdivided into discs, into all these discs that would have a height of delta y. We'd be essentially cutting the oils into small discs and integrating that in order to find the total amount, in order to pump the oil out through the hole at the top of the tank. For a better illustration, let's first draw a cheap drawing of this tank and place it. We draw the tank in a 2D version and place it on a Cartesian plane or on the x and y axis. And the bottom of the tank would lie in the origin of the plane. And if this were a solid of revolution, the rotational axis of this figure would be on the y-axis. And now we'd have to say the radius is 12, so the ends go from negative 12 to 12. And the height of this, if the body were to go from 0 to 24, and then the height of the spout is another 3 meters, so it would go all the way to 27 meters. And the center of this figure lying at 0, 12. Now going back to considering the oil to be subdivided, we have to say that the discs have a thickness of delta y and a radius of x, just because they're both the radius and the height of each disc changes as we're figuring out. So we'd have to place the radius of each disc as a thickness of x, a changing variable. Now let's move on to finding the force. The increment of the force would be the change of weight. So essentially the change of weight would equal, the change of force would equal the weight. And since we're given the density of 9 kilograms per cubic meter, we'd have to say the weight equals the density, 900 kilograms cubic meters, times the volume. That would give us the force, the change of force. For right now, we'd neglect the gravity just because we don't want to confuse ourselves. And now to put it into variables, as we figured out from here, the volume of each disc would be pi times radius squared, radius is x, so x squared, times the thickness delta y, kilograms. Now, if we look at this in more numerical terms, for a circle of radius 12 at its center 0, 12, we need to put this into an equation of x squared plus y minus 12 in brackets squared equals the radius squared. And to simplify this even further, we could say that x squared equals 24y minus y squared. Now essentially this would be the y squared that we would want to substitute into the change of force function, because we want to unite the variables into a single variable, which in this case would be y. So essentially we're plugging this in over here. And now to have a more simplified version, we'd have to say the change in force equals 900 pi times x squared delta y. I'm just rewriting this. And then this essentially would become 24y minus y squared times delta y, because we've plugged this y squared equation into x squared equation, into the change of force equation. And now we move on to finding the increment of force. Now we got to note that the disc has is y meters from the bottom of the tank. What does that mean? That means that from the total height of 27, the total height of 27, the tank must move 27 minus y. The displacement will be 27 minus y meters. So as we learned from our basic physics knowledge, the work, the equation of work, the work function is force times displacement. Now we have the force, the change of force here. So to find the change of work would be the change of force times the displacement that we found here. The displacement we've found here of the tank to be moving a distance of 27 minus y. The disk would be moving a distance of 27 minus y. That would be the displacement in this case. So the change in work, if we now plug in the change of force function, it'll all come together as 900 pi times 24y minus y squared times delta y times 27 minus y in brackets. And now all we have to do is find the integration to find the work required to empty this tank of oil. And because the tank itself is said to be half full of oil, the integration would go from 0 to 12, as the radius is 12. And we essentially just insert this whole change of work function in there, 900 pi. And we could simplify this on the way, or expand this in a way, into 648y minus 51y squared plus y to the third delta y. Right now, delta y would be substituted as dy, as this is an integration, so it would become essentially dy. And to further simplify this, it would become 900 pi, the constant, and the integration would be done as 324y squared times 17y to the third minus 17y to the third plus y to the fourth over fourth, all over 0 to 12. And I've already done the calculation prior to filming, which turned out as 900 pi times 22,464. Now what do we do with this? We're almost there. Now we move this to now add in the gravity. And it says regard pi as 3.14. So now we rewrite this. We rewrite this work equation as 900 times 3.14, which is pi, and gravity 9.8. Gravity, which is g, given times 22,464, and this in 3 significant digits, and we'd write this in scientific notation, is 6.22 times 10 to the power of 8 joules. So voila, we've solved for the work required to pump oil out of the spout in a spherical tank. Thanks for watching.